Hello, this is Tyson Smith with the Space Dynamics Lab in Utah State University. I just wanted to take a few minutes today and share with you some of the work that we've been doing here at the Space Dynamics Lab in Utah State University with regard to small satellite and CubeSat propulsion systems. So the motivation behind this is, as we're all well aware, there's a lot going on in the propulsion market right now with regard in the CubeSat propulsion market. There's a lot of electric propulsion companies out there that are doing a lot of great work. There's some cold gas systems that people are producing, and there's even some monoprop systems that are being built that work really well for the larger ESPA class spacecrafts, things that are in the greater than 1 Newton thrust level. But so what we were interested in is in filling the technology gap that is typically filled by monoprops or chemical propulsion systems by propellants that is a sub 1 Newton thrust or greater than 0.1 Newton thrust, but also you get the same type of ISP, an ISP of between 200 and 300 or so seconds, and which is really outlined here in this orange box. This is really the gap that we are trying to fill. As you look over here, this is your EP systems, and this is your cold gas systems. So that's what we were trying to do. Is we found that there's a lot of missions that just are out of reach for CubeSats right now because there aren't propulsion systems to support those types of missions, mainly RPO type missions, cluster management or formation flying type missions. These types of things are difficult to do because your thrust levels are either so low that it makes it hard to do it operationally, or for a cold gas system, your tank is just so large that it makes it just unfeasible. So that was the goal of the system, was to develop a system with a safe propellant, safe for people to handle, and also has this sub 1 Newton thrust so that we can do these missions that are currently out of reach or extremely difficult from a ConOps perspective with the current propulsion market. A little background into chemical rockets. You have your solid rockets that these are like your bottle rockets where you light them and they just burn until the fuel is gone. You have a solid fuel where your oxidizers mixed in. They're typically not restartable. Liquid rockets are this consists of, when I say liquid rockets, I'm talking about monoprops or biprop systems where you typically have two fluids, an oxidizer and a fuel that are mixed in a combustion chamber and ignited, or just a monoprop that runs through a catalyst and is ignited. Hybrid rocket is kind of a combination of the two. You have a solid fuel, and then you have a liquid or gas oxidizer, and as you mix the two and ignite them. That's kind of what this is. This slide gets into a little bit more about hybrid rockets. If you imagine these black squares are this is a cutaway of a rocket body. These black squares are your fuel. As your oxidizer flows through your fuel port, you essentially erode away your solid fuel, and they combust as they interact, and that's how you get thrust. So as you can probably imagine, if this is a cylinder, as your fuel erodes away, that means your port opens up or your surface area increases, which means that what we call the O to F ratio, your oxidizer to fuel ratio, changes. And as that changes, it means your system is going to be either more efficient or less efficient depending on how it changes. And so what you typically do with hybrid rockets is you try and maximize the time that you're in your ideal O to F ratio. So typically you'll start off with your rocket at the beginning of ignition extremely lean, and then as it burns through this ideal O to F ratio, and then near the end it's burning really rich and less efficient again. And so that's kind of this game that you play with hybrid rockets is try to optimize your O to F ratio. And you can kind of see the O to F shift really well in these images. So this is some still frame images of the burning of an entire rocket motor. You can see over here we're really bright, which means you're really lean. You got a lot of oxidizer in here. But as you go down in time and look at this last photo at the bottom, you can see it's really dark and plumy. There's a lot of fuel that's coming through there that's not being burned because your combustion is less efficient and you're getting you're burning really fuel rich. And so you can really see that change as you look through these. You can see how it changes as you look at these images. And so that's one of the challenges that we wanted to try and address is how can we, keep a consistent O to F ratio. And so, that's one of the challenges that hybrid rockets have that has kind of kept them from being in the in-space propulsion market. Another one is the fact that because the fuel is so stable, so one of the things about hybrid rockets is they're inherently safe, and that's because the fuel is so stable. But because the fuel is so stable, it means they're difficult to ignite. And so sometimes you get to ignite them, a lot of times these pyrotechnic igniters are used that can be susceptible to electromagnetic radiation, but then also can be, dangerous to use. And so these are two of the challenges that we tried to address. This is just wanted to show some images just to kind of reiterate the idea as as the surface area changes or that causes the shift in O to F ratio. As you can see here, beginning before this is a fuel rain before it was fired, you can see the port is really small, and then after firing you can see how big it is. So that really just makes your O to F shift, as you can imagine. So here's the ignition system. The ignition system we use for this system that we're talking about today was originally developed by Whitmore at Utah State University. And how this works, what they found, this was back in 2014, what they found was that if they took a piece of ABS plastic and put some voltages through it, the arcing between two electrodes would not go, would not arc through the air, but it actually would arc through the plastic, and it would release these gaseous hydrocarbons into the port. And if once some kind of oxidizer hit those hydrocarbons, it actually ignited the entire system, and you could essentially, and the thing would essentially stay lit or continue to fire until you turned off the oxidizer source. And they could do this time and time again. You can kind of see, here's the ignition system. You can see it light up as they send some volts through it, and those hydrocarbons right in here. So essentially now you have a restartable, safe, and low power hybrid rocket. Another thing that we found was that at these low thrust levels, your regression or the combustion is dominated by radiative heating. Larger scale rockets, it's dominated by convective heating, but when you get down into these smaller rockets, it's actually dominated by radiative heating. As you can see here, this red line represents radiative heating, the percentage of your regression that's influenced by radiative heating, versus the green line, which is what's influenced by convective heating. Here's what we're talking about, just talking again about trying to control the O to F ratio. What we decided to do is go with an end burning design. You can see here this picture here on the left. If this black is the port, this red is the burn surface area. As you can see at the beginning of life of the motor, your burn area is relatively low, but near the end, the surface area obviously grows. Well, if you go to an end burner, as you can imagine, that's going to stay constant throughout the entire mission, and thus you have more control over your O to F ratio. A little bit about our test setup. Here at the Space Dynamics Lab, we have a propulsion lab where we do our testing. We have this essentially a bulletproof room that's ventilated, and and we can do our test firings in there. Here's all the different propellants that are approved for the lab. Just for the sake of time, I'll go through these next few slides rather quickly. Here's just a little bit about our test cell or our load cell, and a little bit about the data that we are collecting in our propulsion lab that we use to do this analysis. And you can read about all this in the paper if you're interested. But so here's the test results. So here's a diagram of our end burn design. The blue here is your fuel grain. This black here are your electrodes where your ignition system is. And then right here, this kind of silvery square, this is where your combustion chamber is. This is your combustion chamber. Obviously, this is a cutaway model that I'm showing here. So if you can imagine that as a cylinder. And then your nozzle is out here. So here are the results from several tests, from probably over 100 tests overlaid with each other. You can see the rise time was from, essentially from here to here. When you completed the complete rise time, took just over 2 seconds. You can see that a similar on the thrust graph. You can see a similar profile. Interesting to note is the power. You do have 10, 15, maybe 20 watts up to, I guess there was one test where we used 30 watts to ignite the system, but it only lasts for about a minute, and then you can turn it off, and so a relatively low power system. But so something that's worth mentioning is, as you can see, the rise times are maybe not as good as we would have liked. Or if we go down to the next slide, the ISPs are around 140 for the 1 Newton thruster, 160-ish for the half Newton thruster. But our theoretical models, they told us that we were expecting something much higher than 140 for our theoretical models. And when we looked into it a little bit more, what we found is that we were getting a significant amount of heat loss that was getting, heat was getting dropped into the case. You were having heat come out of the combustion chamber and dropped into the ambient air or into the casing, as opposed to being used for combustion. And so what we did, just as a quick test, is we insulated the combustion chamber a little bit better, and we saw significant improvements. As you can see, it jumped up just with the minimal insulating that we did. It jumped up from 140 to about 190. So significant improvements with just some very arbitrary insulating. So what we thought is, well, what about if we use the fuel itself as an insulator? And we came up with this, what we call the sandwich design. And what we mean by that is, you can see in this cutaway model, the fuel is now on both sides of the combustion chamber. So the combustion chamber is the silver, that you see here in the middle, and the fuel grains this is a fuel grain, and here's the other fuel grain. And so using the fuel itself as the insulator, and as you can see, significant improvement in the combustion and specifically in the rise time. Whereas before we were seeing rise times, right here, rise times on the order of seconds, 2 seconds for this one, 1 second for this one. With the sandwich design, that changed to on the order of milliseconds. Power obviously stayed the same, and thrust followed a similar profile to the combustion. And here's the results. You can see the vacuum ISP jumped up to 170 from 140, just with this basic change of splitting the fuel grain onto both sides. So really interesting. Here's a video of one of our tests. You're not going to see a lot here just because the thrust levels are so low. Maybe you can hear it if I stop talking for a second. Just hear the hissing of the motor. And just to finish off the presentation, we've done well over 600 test firings, showed you a lot of those results. Some of the work that we plan to do in the future is continue to optimize the combustion and the O to F ratio with different insulators and different fuel geometries. We also want to start looking at smaller thrust levels like a quarter Newton or 0.1 Newton. We also are going to try some different oxidizers, specifically peroxide and nitrous oxide. And then another thing we're going to do over this next year is build and test a qual unit that can be used for flight. And that brings us to the end of my presentation. Thanks. Let me know if you have any questions.